For this next problem, we're asked to find a function of the horizontal displacement of the ball as a function of its angle of release theta. To do so, we're given that the length of the arm here is L and that the height of the shoulder is h. We're also given the initial speed from which the ball is released, which is v. This is a classic kinematics problem. We're going to use the principle that the acceleration in y is equal to minus g, but in the air, the acceleration in x is 0. To solve the problem, we're going to use the equation delta y is equal to v initial in y times delta t plus 1/2 acceleration times delta t squared. With this equation, the only unknown that we have is the time. So we're going to solve for the time and use it to find the horizontal displacement with the equation of motion, which is that delta x is equal to the velocity in x times delta t. So with these two equations, we're going to be able to answer the question here. Don't forget that the vector v here can be decomposed into its components. So we have vi y here and v initial in x. V initial in x, since there's no acceleration, will remain constant, so we can just call that vx. And we have the angle theta here, so we know that v initial y is going to be v sine theta, and v initial in x, which is just vx, is going to be v cos theta. So we can start by plugging numbers into this first equation. So we know that delta y, the vertical displacement, so the ball starts at the point here, at the end of the arm, and goes all the way to the ground. So the vertical displacement is negative, and it's equal to distance h here, plus the height provided from the arm, which is going to be L sine theta. So delta y here is going to be L sine theta plus h, but negative. Then the initial vertical velocity is, as we obtained previously, v sine theta, and the time is our unknown, so we don't know it. The acceleration here is minus g, so we can rewrite this part as minus g over 2 delta t squared. Now this is a quadratic equation. If you haven't noticed, we have all of the terms here are constants that are given, except for theta, which is given but not a constant in our problem. So we want to isolate for delta t. So we're going to put all of these in the same side. So we're going to bring these two terms on the other side. So we get that g over 2 delta t squared minus v sine theta delta t minus L sine theta minus h is equal to 0. So now we can solve this quadratic equation with a quadratic formula, since we have the terms here ax squared plus bx plus c equals 0. So we can solve for delta t, which is equal to b to minus b. So in our case, b is negative v sine theta, so minus b is v sine theta, plus or minus square root of b squared. So b squared is just going to be positive v squared sine squared theta, minus 4ac. So 4 times a is g over 2, and c is minus L sine theta minus h. And all of that is over 2a. So a is g over 2. We can rewrite this part here as v sine theta plus or minus square root of v squared sine squared theta. Here, the 4 cancels out with the 2, so we only have 2 left. And we can get the minus out of this parenthesis and multiply it with the minus here, which will become a plus. So we get 2g L sine theta plus h. And in the bottom here, we just get g. Here, if we look at the 2 times which we expect the ball to be at 0, it would be at this time here. And if we go back in time, this curve would get to 0 at a negative time here. So we're going to look for the positive time. To get this positive time, we're going to need to do v sine theta plus this square root. If we had done minus this square root, we would get the negative time. So delta t positive, which we're looking for, is going to be v sine theta plus square root of v squared sine squared theta plus 2g times L sine theta plus h over g. Now we've found the time, and all we need to do is plug this time into the equation to find the horizontal displacement. So delta x is equal to vx times delta t. And since the speed is constant, and so we're just going to plug vx, we remember, is v cos theta, as we found out at the beginning here. And delta t, we just found it, so it's going to be v sine theta plus square root of v squared sine squared theta plus 2g L over g. Now we can just keep it like that, or we can get the g out of this parenthesis here, since it multiplies everything up, and we just get v cos theta over g times this, and that's the function for the horizontal displacement as a function of the angle.